Okay, so Matthias is one of the key people behind the ultimate Automizer. He did his PhD in 2015 with Andreas Podolsky, and his work on ultimate Automizer has led to 26 gold medals over 6 years, 26 medals over 6 years, including gold medals at SVComp. So, Matthias.
Yeah, okay, thanks for the introduction. In this talk, I would like to present you the algorithm that is underlying this Ultimate Automizer tool. And so the Ultimate Automizer is a tool for checking non-reachability, memory safety, termination, and overflow. So several properties, not only safety properties of C programs. And we participate regularly at this SVComp, the software verification competition, and we're quite lucky this year that we got some medals. Okay, and I would like to intrigue you with some motivation about the underlying algorithm that says that we have a new paradigm that says that a computer program is just a collection of statements, and the definition of this program consists of two completely different parts. And I think one of the successes of our tool is that we separate these two parts. And so one part is the meaning of statements of this computer program, and the other part is how the statements are arranged. And so the meaning of these statements is defined by the semantics of the programming language. And the way how the statements are arranged in a concrete program is defined by the control flow graph. And so we use two completely different formalisms for this. And so one is SMT, so logic for the meaning of the statements, and we use automata theory for the control flow of a concrete program. Or, yeah, let me phrase this differently. We say we have a new view in programs that says a program defines a language over the alphabet of statements. So we say a program has some language, defines some formal language, and the basis for this is some alphabet. And statements, like you see here, some assignment statements or assumed statements, are just considered as symbols of an alphabet. Okay, and then the control flow graph, this is an automaton over the alphabet of statements. And since we want to do verification and we check properties, we encode them as error locations, and we say error locations are accepting states of this automaton. Okay, and so here you see the running example that I want to use in this talk. So here given as pseudocode and as a control flow graph, and it's a control flow graph with some special location. This is an error location, and we will consider this as an automaton. Okay, and we will say this is an automaton that defines some language, and the language are sequences of statements, and these are then all sequences of statements that can potentially reach the error location if we completely ignore the semantics of statements. So if we just consider the control flow. Yeah, maybe let's go quickly through this program. So it has two variables, one variable n, you can think of this as an integer variable, and one variable p, you can maybe think of this as a pointer. And at the beginning, we assume that this pointer is not 0, and then in a while loop, we decrement n, and in the very last iteration, we set p to 0. But at the beginning of each iteration, we check whether p is 0, and we say the program is correct by definition if p is here never 0. Okay, and obviously this is a correct program because the pointer is not 0 at the beginning and set to 0 only in the very last iteration, so it can never be 0 here. Okay, and before I want to show you how we verify this program, I would like to show you some completely other program. So in our formalism now, this here is also a program, and a program with a specification because it has an error location. And now you may wonder whether this is a useful program because, for example, at this location, there's a solve loop labeled by several statements, and it's not clear how pseudocode of this program would look like. And yeah, what I want to say is, well, it doesn't matter, but we need programs like this that look completely useless in our verification algorithm, because we will apply set theoretic operations to programs. Okay, maybe this is all this was a bit confusing, but let me show you the our approach on an example, and maybe then things will get clearer. So again, we have here our running example, and now our algorithm first checks whether this error location is reachable in a graph theoretic way or another automata theoretic way. So we can just apply some emptiness check for a finite automaton here, and we will get this word consisting of these three statements of this three letters. And yeah, well, you will see this is not a real counterexample to this program because the program is correct. So as a next step, our approach, well, after it took this sequence of statements, and we call the sequence of statements a trace, we consider now this sequence of statements as a program, because we say every language over this alphabet of statements can be a program. So here's, it's a very simple program where we can give in some pseudocode. And now the next step is to analyze this program. Oh, and yeah, I would like to show you here a small excursus about how we're checking, how we find correctness proofs for straight line codes. And so this is, we use an SMP solver and yeah, encode this somehow as an SMP script and get these, get an annotation. We call it a Floyd-Hoare annotation that is a correctness proof for this program. And here you see a correctness proof given by symbolic execution. This is a proof that will be not very useful for us because it is very, it's very precise. It contains all details that are maybe not important. And in practice, to avoid this, we use something called crack interpolation. So we like very much SMP solvers that support this interpolation, and then we can get a Floyd-Hoare annotation like this here by using this get interpolants command. Okay, so yeah, first step was we take some trace by just purely automata theoretic algorithms. Then we consider this trace as a program and analyze the correctness of this program. And here in this case, the program was correct, and we have here a Floyd-Hoare annotation that shows correctness of this program. Okay, and now comes the crucial step of our algorithm, or one of the crucial steps. We will next generalize this program. So we have now a correct program, but the next step is to enlarge this program. But we will not change the proof. So we fixed the proof for this program, and now we are going to enlarge this program by adding new statements. And we want to add new statements, or new edges, I should say, in this automaton, labeled with statements, and we want to add only new edges that make still sure that this is a correct program. And we can achieve this by adding only new edges if the corresponding Hoare triple consisting of annotation of the predecessor, statement, and annotation of the successor is a valid Hoare triple. And if we do this, we still have a correct program. And so here in this example, we will now do this for several statements, and we add here some self loops. And yeah, we can in fact add the self loop for every statement, but the statement that modifies, that sets p to 0. Okay, and we will do this for all the other locations. And so here it's just coincidence that we add only self loops. In practice, we may add arbitrary edges as long as the corresponding quadruple is valid. Okay, and now what we have is the original program for which we want to analyze whether it's correct or not. And we have a new program that is correct, but now, yeah, this is a complete, or yeah, it's a rather completely different program. And now the next step of our algorithm is we consider them now in a purely automata-theoretic way. So we are going to check the set theoretic difference of these two programs, because this program defines a set of sequences of statements that can potentially lead to the error location. And this here, it defines a set of traces that are not executable, or that are correct, or that can never reach the error location. Okay, and we check this by using purely automata-theoretic methods. And in this example here, the set theoretic difference is not yet empty. So what we can then do is, well, we continue in the same manner again. We take now some trace that is in this set theoretic difference. So it's a trace that can potentially reach the error location, or that can reach the error location in this control flow graph if we ignore the semantics of the statements. And yeah, then let's continue by analyzing this trace again. So we take this trace, we consider this trace as a program, we analyze the correctness of this program, and we generalize this program by adding transitions. And we may add a transition whenever the corresponding triple consisting of predecessor annotation, statement, and successor annotation is a valid quadruple. And we may also merge locations if they are annotated by the same statement. Okay, and now we have the original program and two programs that are correct. And we apply again our automata-theoretic methods. And in this case, we are lucky. And so we have proven that this program is correct because this inclusion here holds. And yeah, the reason for the correctness is that every sequence of statements that can lead in the error, that can lead to the error location is a sequence of statements that is in one of these correct programs. Okay. Yeah, next I would like to quickly go through our verification algorithm. So we have here this loop. We start with a program, and we have here at the beginning an empty sequence of correct programs, and we check whether the language of the original program is a subset of these languages. Yeah, at the beginning this is empty. Then we pick some error trace. We check whether this error trace is feasible. And if it is feasible, well, then the program is incorrect. But if it is not feasible, well, we generalize the infeasible, we construct a proof for this infeasible trace because we consider this infeasible trace as a standalone program. And then we generalize the program to a larger program and add it to this set here of programs for which we then check whether the traces of the original program are already included here. And if this inclusion holds, then the program is correct. Okay, yeah, then I would like to use the remaining time to talk about interprocedural analysis. So if we want to consider a program with several procedures, then we have the problem that regular languages are not sufficient. Because, well, if we have a regular language, we cannot enforce that this call and return discipline of the specification of this programming language is kept. And so we could have very weird programs like this. And a solution for this is, or could be, that we use context-free languages and push-down automata, but the problem is they are not closed under intersection. So the corresponding class of languages is not closed under intersection. And so we would not be able to apply our algorithm. And so a solution for this was to look at other automata types. And there are these nice visibly push-down automata implemented by or developed by Allur and Madhusudan. And there we have different kinds of letters in the alphabet. So some letters are call symbols, some are internal symbols, and some are return symbols. And if we use this, we can make sure that this stack discipline is kept. And so then we can implement some recursive program like here this, or we can represent some recursive program like here an implementation of this McCarthy function by such a visibly pushdown automaton. And these visibly pushdown automata have Fourier return relations, and these make sure that the stack discipline is kept. Okay, this is one challenge for interprocedural programs. Another is, well, what is the Floyd-Hoare annotation for such a visibly pushdown automaton? And so one option is we could try to proceed with states that also talk about the stack. But the problem is then the locality of this annotation is lost, and it will be very difficult to generalize this program. To generalize a program for which we have a proof. Another option seems to be we use only the local valuation, but this will not work because then the dependency between calls and returns will get lost. And so our solution to this is we compute proofs along traces that we call nested interpolants. And there we have something that we call Hoare quadruples. So for return statements, we need two predecessors. And one is the local state of the caller. And the other is the state or the annotation of the callee before the call. And we can put these two together with the return statement to the annotation that has to hold after the return. Okay. And we can then have Floyd-Hoare annotations for these visibly pushdown automata that are suitable for recursive programs or for interprocedural programs. And we can get rather local proofs that can lead to a generalization of these programs. Okay, I'm not sure how much time is left.
So yeah, I think you have another minute or two.
Okay, then I would like to say that I'm very proud that this approach has also been extended by other people. So there's another extension to interprocedural programs. There have been extensions to concurrent programs, to time systems, and to solving horn clauses, and the approach there uses tree automata. And we ourselves also implemented some extensions, one for checking termination and LTL properties, and there we use Bücher automata, and another one for concurrent systems where we use Petri nets. Yeah, okay, then I would like to thank you for your attention.
Great. Thank you, Matthias. That was very clear, and you did really well on timing as well. So any questions? Feel free to chime in or raise your hand.
Maybe I can ask
Roderick?
Yeah, so I wanted to ask if you find bugs in your program, whether you can use the same mechanics to find fixes.
We have not yet implemented something there. Maybe, or maybe some people in Israel, so Batjen Rothenburg, had some ideas on this, but I think she hasn't published them yet. But so I have not done any work on this yet, but I think this is an interesting research direction.
Okay, thanks.
Martin?
Hi, Matthias. Thank you very much for the talk. Very interesting stuff. Possibly unhelpful question. The frame part that you did with the or quad on the return statement, isn't that a separation logic type thing? Isn't that there a star implicitly in there somewhere?
I have not thought about this in this way yet.
I'm not sure if it's a helpful thought. But,
yeah, thanks. I think I have to think about this a bit longer. So there might be some connection between separation logic, but I never considered it as this.
the other one that came to mind, of course, was the interpolant algebra, the language type restrictions on interpolants, because the point is you've got res equals x and x in the caller, and you've got that's a shared term in interpolant sense.
Yes, so,
help, but thank you.
yes, on practice, we compute these interpolants by tree interpolation. But luckily, some SMP solvers support this.
So, Matthias?
Yes.
I have a question. Are you able to reuse proofs from, a library, for instance? I mean, it may be that the traces that you're constructing, you've already seen examples of these elsewhere, and that you could bring in proofs from a library.
Yeah, so you mean I could keep all traces that I found so far that are correct in some database and then check whether they occur again.
Yeah.
Yes, and so this is definitely interesting. We have thought a bit about this, but we never implemented this so far. Yes, so if it's really the same library, yeah, then this would probably work. Yeah, in fact, what I had in mind is that you're suggesting that we go from one library to another, because maybe some reasons for infeasibility may be very similar. But variable names are different, and then we would need something like alpha renaming, or I'm not sure if this is the correct term, but the variable x in one library might be a different variable in another library, and there may be a lot of choices how to replace these. Yeah, and I think this is an interesting question, but we have not really started on this yet.
So Ranjit has a follow-up, and then I'll go to Supratik. So Ranjit first.
I was just following up on, my video is off. Can you, I guess, is there some way you can save the, what did you call them? The push down automata that you get for some function. Let's say you have the function foo that's used in 25 different programs, and somehow I've analyzed it once. Can I save the push down automata for foo and reuse it across different clients? I think
yes, definitely. So so this is possible. I should have said, we already did some work there where we really used the very same library or the very same automaton or the very same summary. And yeah, this can be done. And in some cases, it saves a lot of time if the summary works again for a different specification. But we also had cases where it was just a waste of time because the summaries did not work, and to look up all these summaries costed more time than it saved.
So you mean the problem was the summaries didn't really generalize across, they weren't general enough to be applicable across the different clients?
Yeah, it depends from program to program. So in some cases, they were general enough and sometimes not. And yeah, I think that's it. So we got some speed up, but I think, yeah, maybe we should, we have to try it on larger programs. So yeah, I think it would be especially interesting to verify a software project over time. So where you have new commits every day or so. And then I think it's possible to reuse a lot of this old information. But we have not tried this yet on a larger software project.
Yeah, hi Matthias, very nice talk. I want to ask that when, in this slide that you're showing right now, when you have nested interpolants, so is there a specific kind of logic that you use for this? For example, if I'm reasoning about, programs manipulating dynamically allocated memory, I mean, would you need separation logic, interpolants and separation logic? I mean, is there a specific logic that you use for these nested interpolants? Because it does look like that, different logics allow you to, maybe specify things that are relevant that you want to say.
Yes, so in practice, we use SMT theories of dissolvers that can provide interpolants. Or well, we have some techniques where we can get something similar as these Craig interpolants by using unsatisfiable cores and symbolic execution. But so the theories that we use are, for example, the combination of bit vectors, floating point arithmetic, and arrays, or integer arithmetic and arrays.
But is that sufficient? I mean, I guess, I don't think we have things like separating conjunction or the magic wand in SMT theory.
Yeah, so we do not use separation logic.
Okay.
So maybe this would be a good idea for the future, but at the moment we do not use it. Maybe we use something very similar, and you could view all this as separation logic. But I'm not familiar enough with separation logic to definitely say that this is just another form of separation logic.
Okay, thank you.
Okay. Thanks again, Matthias. So I enjoyed the talk, and we'll switch to the next talk.
Yeah, thank you.